all unit, we've been focusing on different types of waves and their applications. And so far, we've been primarily looking at sound waves and other forms of what we call mechanical waves, waves that require a medium in order to travel because the matter is physically vibrating. Today, we're going to talk about a different category of waves. These are known as electromagnetic waves. More commonly, we think of these as light waves. Now, the way we experience light typically is visible light, light that our eyeballs are able to sense, but there are many, many different examples of electromagnetic waves that we can't always interpret in the same ways. So today we're going to talk about light, but we're also going to talk about the different categories of electromagnetic waves that are important in our lives as well. Now, frequency is going to have a factor with light in the same way that frequency affected our sound. If you remember when we talked about sound, when we change the frequency of a sound, we change the pitch of that sound. So it's kind of like going up the scale on a piano. What you're doing when you're changing notes is you're changing the frequency of those sound waves. Now, light can also change its frequency. And if we're talking about visible light, a change in the frequency for visible light is changing the color of that light. Now, frequency and light are really hand in hand with this idea of color. So if you increase the frequency of your light, you give it more energy and go more towards the violet part of the spectrum. Now, you can probably predict how these different colors are related to each other, and they're actually in the order of the rainbow. So if you know your Roy-G Biv, you're able to interpret pretty easily how these colors are relative to each other. Now, a lot of times, instead of frequency, these different wavelengths of light are interpreted as a wavelength in nanometers. And you can actually create any different color of light using a nanometer wavelength as seen here. Here's a great example of what that wavelength to color relationship actually looks like. On this website, there is a slider that allows you to change the wavelength that you're talking about. Notice as I increase the wavelength, I'm going from purple all the way to red. Now, just like we see a spectrum of colors in our rainbow, we see a spectrum of colors as we are changing the wavelength. The lowest wavelength is purple, that's the highest frequency, and the longest wavelength is the lowest frequency, that is a deep red. So if light has a frequency and light has a wavelength, light must also have a speed. Now, the speed of an electromagnetic wave is going to be pretty constant. We'll talk about some differences later on, but for the most part, we refer to the speed of an electromagnetic wave, the speed of light, as the speed that that wave travels in a vacuum. A vacuum here just meaning no matter is present, so like the vacuum of space. Now, it's been determined experimentally that the speed of light is just over 299 million meters per second. To put that into reference for you, the speed of sound is about 340 meters per second in room temperature. So this is about a million times faster than sound. This is too exact for our purposes right now. So when we use the speed of light, we are just going to round that to 3 times 10 to the 8th meters per second. You'll notice here we are using the symbol c. The symbol that we use in an equation to represent the speed of light specifically is going to be this lowercase c. And you may have actually seen this before in a very famous equation by Albert Einstein, E equals mc squared. This c is the same as that c. So the speed of light squared. So this speed of light, while it's very, very fast, much, much faster than sound, it isn't instantaneous fast. So the sun is about 150. Now, this speed of light, while it is very, very fast, much, much faster than the speed of sound, it is not instantaneous. The sun is about 150 million kilometers away from Earth. So it actually takes light from the sun a certain amount of time before it gets to the Earth. And we can calculate what that is just using the simple velocity equation that we used many, many units ago in this semester. So the velocity is distance divided by time, meters per second. If I wanted to solve that for a time to figure out how long it takes the light to get here, That time is just distance divided by velocity, just multiplying both sides by t, and then dividing both sides by v. Now the distance is going to be this 150 million kilometers, but we're going to convert that into meters so that we can use our velocity in meters per second. Now that's the same velocity that we saw in the last slide, the speed of light, 300 million meters per second. Now if I do that division, I end up getting a time of about 499 seconds, almost 500 seconds. Go ahead and calculate real quick, just pause the video and figure out how many minutes is that. So if you do a simple calculation, divide that 500 seconds divided by 60, you'll get that it takes about 8.3 minutes for light from the sun to get all the way to the Earth, which means that if for some reason at this very moment the sun stopped emitting any light, we wouldn't find out until over 8 minutes later. We could still look up at the sun and see the sun there because we are looking at light that is 8 minutes old. And the same thing happens when you go farther and farther out. It turns out that many of our stars are millions of light years away from us, which means that when we're looking at the stars, we're not looking at what the stars look like now. We're looking at what they look like millions of years ago. It takes light that long to travel if it is that far away. So this is a diagram of what a light wave looks like. We call it an electromagnetic wave because it's actually two different fields that are oscillating perpendicular to each other. A magnetic field and an electric field, electromagnetic. And you can see that this oscillation is perpendicular to the direction of this travel. Remember to yourself, we had these two categories, transverse or longitudinal. Which one is an electromagnetic wave given that description? So if you remember, one of these waves oscillates parallel to the direction of motion, and one is perpendicular. The perpendicular one is a transverse wave. Longitudinal is a good example of like a sound wave vibrating back and forth in a pressure wave, but transverse must be oscillating perpendicular to the direction of motion. Light is transverse. So I mentioned earlier that light is only part of this overall electromagnetic spectrum. Now, we're going to talk now about these different other categories within this spectrum because, as you can see, visible light is just a tiny sliver of this. And if you increase the frequency or change the wavelength slightly from that visible light, you actually create a form of electromagnetic wave that is related to light but can't be sensed by our eyes. It's still there. It's just being sensed in different ways. So going at this, starting from the most energetic wave, gamma rays are often formed in space by exploding supernova or different high energy events. Here on Earth, the time that we see gamma rays most often is in nuclear decay. Some gamma radiation can be emitted from a nucleus as it spits off an alpha or a beta particle. These gamma rays are very, very high energy, and they are high energy because their wavelength is so small and their frequency is so high. That high frequency means it packs a lot of energy for a given amplitude of that wave. We don't see a ton of gamma rays in applications, so we're going to move on to the next example. X-rays you're probably familiar with. X-rays are our next most energetic wave. And you probably have some sense that X-rays could be dangerous because if you've ever had an X-ray, either at the dentist or if you had a broken bone, they will typically have you wear a lead vest. And the reason for that is X-rays are energetic enough that they could damage some of your organs. That X-rays can mess with some of the cells and cause mutations that can eventually lead to cancer. But X-rays can be very useful for us as well. X-rays don't travel through bones as well as they travel through flesh, which make them a great way of basically seeing inside our bodies to see what our bone structure looks like, if you've broken a bone or if there's something else going on. But again, X-rays are pretty high energy and something that you should not be exposed to at a high level, or you could cause some long-term damage. Now, the next most energetic is now something that we are starting to experience more of on an everyday basis. Ultraviolet light is the same light that we get from the sun, in addition to some of the visible light that we see. Now, ultraviolet light is what's responsible for you getting tan. It's also what's responsible for you getting sunburn or skin cancer later on. Now, the ultraviolet light from the sun is categorized as UVA, UVB, and UVC. Each of these are different frequencies within that ultraviolet part of the spectrum and have different impacts on what they do to your skin.
If you're outside on a beautiful summer day, chances are you need to have some sort of sunscreen protection. Now, all sunscreen actually has a rating on what types of UV light it cancels out. So here, let's take a look at this sunscreen bottle and see what the rating is. For this particular sunscreen, we can now look at the bottom here and it says that it has UVA and UVB protection. That means that it's going to be able to block out those harmful UV rays that are able to make it through the atmosphere and could potentially cause skin damage later on.
We can produce our own ultraviolet light as well, as many of you have maybe seen before in either a tanning bed or a black light.
One application that you've probably also experienced ultraviolet light is in black lights. If you've ever been like cosmic bowling before and you've seen the black lights that are on the wall, these black lights, they glow to our eyes in kind of this purplish light. They're not black at all. The reason that they're purple is because purple is the closest color to ultraviolet in that visible light spectrum. So part of that light is going to be a little bit purple because these are right on that border. Now, something about ultraviolet light that is important is it is a higher energy light than visible light is, which means when it strikes something, usually when it's white or light colored, it's actually exciting some of the electrons inside that material. And when those electrons fall back down, they are emitting their own light, which is why my white bow tie here is glowing very strongly. My teeth are glowing. Really anything that's white. Here in my workshop, you can see a variety of different things on my workbench are also glowing white in the presence of this black light.
This ultraviolet light is very, very high energy as well. It is more energetic than the visible light, but it's very close to the violet or purple part of our visible light spectrum. So the next part of this electromagnetic spectrum is visible light. We finally made it to the part that our eyes are able to sense, one of the main ways that we interpret our world. Now, visible light is broken down into these different colors, and the difference between the colors, as we mentioned before, is defined by their frequency and their wavelength. That the red light has the longest wavelength and violet light has the shortest wavelength. That also means that the red light has the lowest frequency and violet has the highest frequency, which is why ultraviolet is more energetic than infrared, which we'll talk about next. This picture here is a great model of this, that you can see a couple different things coming from this. Number one, they're all moving at the same speed. All light, no matter what the color is, travels at the speed of light. But there is a difference. There's a difference in the length of their wave, and there's also a difference in their frequency. If you watch that red going up and down, it doesn't bounce as many times per second as that blue one does, because blue is a higher frequency. Now, with that higher frequency, we get a higher energy as well. One of my personal favorite things to do with light is related to lasers. I've got lasers of a variety of different colors, and those different colors produce different amounts of energy. So here's a video of my green laser, and this green laser has more energy than your typical red laser that maybe you've seen before. Here's a great example of that high amount of energy. I also have a pretty low-powered violet laser, and while its amplitude isn't very high, it's not very bright. It has enough energy that it's able to excite the electrons that are inside a fluorescent material, and you can make something that typically glows in the dark glow in the dark instantaneously. So here's a video of me using my purple laser on my glow-in-the-dark skeleton decoration. The next wavelength of light that we have in our electromagnetic spectrum is infrared light. Now, you've seen infrared light in a variety of different circumstances potentially. One that we often think of for infrared light is infrared light being emitted as heat. So right now, if you have a body temperature at all that is above 0 degrees Kelvin, you're emitting infrared radiation. Here is a picture of me at a wedding that was at a science museum where I am emitting infrared light, and this camera is able to represent that. Here is a little video demonstration of using an infrared camera to talk about the different heat.
If I take these two glasses of water, they look pretty much identical in every way. They're both very clear, and they're both just normal water. And in the visible part of the spectrum, that's true, that these are exactly the same. But as you can see in the infrared, there's a clear difference between these two. This one on this side is significantly hotter than this one over here. And we can see the difference because of the different wavelengths that are being emitted from the hot versus the cold or room temperature.
Infrared doesn't have to be heat, though. Some infrared is used in form of LEDs to transmit information. So here are some examples of some infrared that you might have in your house right now.
There are many different devices that use infrared light to transmit information. So one example is a simple remote. So you might have a remote at home that looks like this, and you'll see that there's a little LED on the end of it. And if you push a button and you look at that LED, you're not going to see anything because this LED is not emitting visible light. Instead, this is emitting light in the infrared part of the spectrum. Now, some cameras, like the Android phone that I'm using right now, actually don't filter out all of the invisible infrared light and allow you to see that light. And if you take that remote while pushing any button looking at that LED, you'll see that it will start to flash. Now here, that color that you're seeing doesn't really mean anything in particular. With my eyes, I don't see anything coming out of that LED. Instead, this is just the camera's filter not filtering out that wavelength. You'll see that it's pulsing. Now the pulsing is just transmitting information in ones and zeros in this wavelength that you're not able to see, but the receiver on the other end can sense that. Some products use infrared light in order to let you see in the dark. So this isn't using like thermal infrared like we were seeing in that infrared camera. Instead, it's using infrared LEDs like the one that we saw in the remote. This is a baby monitor that allows you to see your child even if it's dark in the room. And the way it works is there's this circle of LEDs that right now don't look like anything because those LEDs are emitting infrared light. So we're going to actually turn off the lights here to activate those infrared lights so that you can see what's going on. So with the lights on, you don't see anything in particular because the camera is set to use that visible light in order for the camera to work. But if I turn off the lights, you'll see that those infrared lights start to glow. They turn on, and again, my camera is able to see it because it's not filtering out that infrared part of the spectrum, but my eyes don't see anything. To my eyes, basically, that camera is just in the dark. If I turn the lights back on, we see that those infrared lights turn back off, and it's just using the visible part of the spectrum again.
Microwaves are the part of the electromagnetic spectrum that's just a little bit longer in wavelength than the infrared light. Now, microwaves are most often thought of in terms of a microwave oven. Now, in this case, it uses microwaves, the energy from those microwaves, to actually vibrate water molecules that are in your food. And the vibration causes an internal friction to heat up the food. Now, in practice, we actually use microwaves more for something else. If you have a phone or an iPad or a laptop right now that's connected to Wi-Fi, like my phone is right here, it is using microwaves in that part of the electromagnetic spectrum to actually encode the data that you are uploading or downloading. So within that wave, you are storing that data that you're transferring back and forth. Another form of transferring data from one place to another is often used in the radio wave part of the spectrum. Radio waves are most often thought of, yes, in radio. So if you are dialing into your favorite radio station in the car, you are using radio waves to interpret that information. If you use an antenna for your TV, you are also using radio waves there. Now, there are a variety of different examples of wavelengths and frequencies that are used to transfer this data. The United States actually has allocated different parts of this spectrum to use in different ways. And this map here uh, partitions all of these different parts of the microwave and radio wave part of the electromagnetic spectrum for different uses. Now, this is super hard to read, so let's actually look at one part of this that you have probably seen before. We're going to look at just this chunk of this part of the spectrum. And you can see here, this is the part that's responsible for FM radio. And you'll notice that these numbers here are actually in megahertz, so million hertz. The FM radio broadcasting has been allocated the part of the spectrum from 88 megahertz or 88 million hertz to 108 megahertz. Now, those numbers might actually sound familiar. If you've ever tuned in your dial on a car radio, you have seen that your car can really only go between 88 and 108. So all the radio stations that you may be able to think of right now off the top of your head probably have a number somewhere in there. That number isn't just a random allocation. It is actually the frequency at which that radio station is being broadcast at. So when you are tuning your car, you are tuning into that particular frequency to get the radio station that you want. You'll also notice that the TV channels 5 and 6 are right next to that. I've heard stories of people modifying their radios that they can tune into a lower frequency and actually tune into one of the TV channels instead of one of the radio channels because they are broadcast at neighboring frequencies. So from this list, you should be able to name these different types of electromagnetic waves. Now, starting with radio, then microwave, infrared, visible, ultraviolet, X-rays, and gamma. This list is in order of increasing energy. The higher the frequency is, so gamma being the highest and radio being the lowest, the more energy. And typically when we talk about these types of waves, we often reference like the danger of them. So ultraviolet and X-rays and gamma rays have some inherent danger that can maybe mess with the cells in your body. But we also talk about other aspects that radio waves and microwaves don't necessarily need a high energy in order to be useful. That we can transmit data just like we do with Wi-Fi and radio stations over these lower frequency, longer wavelength types of waves.